So far, we have seen quite a few similarities between univariate CDF, where only a single random variable is involved, and multivariate, or as a special case bivariate CDF, where more than one variables are involved. Now we shall see one important aspect with respect to which univariate and multivariate CDF differ. Consider two statements. One, the univariate CDF fx is continuous everywhere. And two, for every point A in R, probability x equal to A is 0. For univariate CDF, we know that 1 and 2 are equivalent. If 1 holds, then 2 must hold, and if 2 holds, 1 must hold. We have seen this in our probability 1 course. Now consider the analogous statements in case of bivariate CDF. The first statement is as before, fxy continuous everywhere. By everywhere, I mean over R2. And the second statement is every singleton set has probability 0. Whatever a comma b you choose in R2, probability that x equals that a and y equals that b is 0. But now, these two statements are not equivalent to each other. In fact, 1 still implies 2, but 2 does not imply 1. Let us prove this implication as a theorem. We start with xy having CDF xy, fxy. We take any point AB in R2. Now, instead of assuming that f is continuous everywhere, I will just assume that fxy is continuous at the point AB. That's enough. Then, the probability that x equals a and y equals b must be equal to 0. The idea of the proof is best understood through a diagram. Here is the point AB. I am trying to find out this probability, but we know that the CDF is a very good tool to find out probabilities of rectangles. So we will make a little rectangle over here. By taking some x less than a, some y less than b, in that case we can find out the probability of this, and then we will let x go towards a, y go towards b. They should increase to a and increase to b. Then this rectangle will dwindle to just this singleton. Accordingly, we take two sequences, xn and yn, xn going towards a and yn going towards b. Then we shall employ our familiar trick, that 4-term thing, which will give me the probability of this particular rectangle. Now, as xn goes to a, yn goes to b, this thing, this event will go to this event, decrease to that event. And so, by continuity of probability, this thing will converge to the probability here. But since I have f continuous at AB, so the limit of this equals FAB, limit of this is also equal to FAB, and limit of this is also equal to FAB. Since there are 2 plus terms and 2 minus terms, they cancel off and give you 0. As a result, you get the theorem. Next, we need to discuss a counterexample for the converse. That is a counterexample for this statement. Even if for all AB the probability of the singleton point is 0, still fxy need not be continuous everywhere. And we will construct this counterexample as an exercise. In this problem, I am giving you two jointly distributed random variables where x is Bernoulli half and y has density given by this. 1 if x lies between 0 to 1 and 0 otherwise. I hope you remember what is meant by Bernoulli half. It means that x can take only two values, each with probability half and half, just like tossing a coin, tossing a fair coin. Now when I tell you only distribution of x and distribution of y, I have still not specified the joint distribution. In order to do that, I further tell you that x and y are independent. Your first job is to find and sketch the CDF f subscript capital X of x. And then you are required to do the same thing for y. In case you have forgotten, I will quickly remind you that fxx is probability x less than or equal to x. And similarly, fyy is probability y less than or equal to y. Then the joint CDF of x and y, fxy, is by definition probability x less than or equal to x and y less than or equal to y. Now this is something in terms of x, this is something in terms of y. They are combined by and x and y are independent. Hence, the probability splits up into two probabilities, one in terms of x, the other in terms of y. Now we see that this is precisely fx and this is precisely fy. So once you have computed these two, you have in effect also computed the joint CDF. Now the joint CDF is defined for every x comma y in R2. I want you to write down the formula, whatever you get after doing the product, in this xy plane. So where you will use what formula. For example, I will do one for you. This will be equal to 0, which means if you take any xy here, the probability that x is less than or equal to x and y is less than or equal to y, that is 0. That is obvious because it can only take values, y can only take value between 0 and 1 and x can only take the value 0 and 1. So probability that it is less than or equal to this is 0. Similarly, you fill in all the other cells. Then check if the fxy that you get is that continuous. And finally show, this problem you can do just directly looking at this, that whatever AB you take, probability x equal to A and y equal to B must be equal to 0. So it's a long sequence of problems, but it eventually gives you a counterexample that even if this holds, this is actually not continuous. You will find that it is not continuous.